Really? Ooh. Hi guys, just trying to set up my cell phone. All right, hopefully everyone's doing okay. Running a little bit late, just a couple minutes here. Let me get everybody in here. Okay, well, let me begin here. Turn off my light, too much reflection here. Okay, just a couple of quick notes. Just be aware that a reminder that there's an exam coming up online. Okay, so you have it available to you a little bit over 2 days. Okay, so it's open up on midnight and it ends, what, 2 days later at 11:59. The other thing too, I know this is all new to a lot of us as far as online instruction. A lot of pros and cons about it, but I really would like to get some feedback from you. So if you have time, um, uh, shoot me an email. Tell me, give me some suggestions of what you think might be better to present this material. Some sessions are basically on your own, follow the text and then take the exam. Some have a limited number of video sessions. I went the other route. I figured I'll do the full time, and because that's this semester being kind of broken up a little bit, I figured we've been used to the full time is continue. Either way, this summer I'm doing the 1:30 again. It's all online. I'm appreciate any some information from your end, what you think can be done better. Uh, but if you got time, just shoot me an email. I will appreciate it. Okay. Well, don't forget your homework due dates. Keep an eye on Canvas, and we're gonna knock this chapter out pretty quick. It's a small chapter, and it's kind of related to. I introduced bits of it to everyone when we were balancing equations. This is where balancing the equation is important because we're going to get information from the balanced chemical equation. So let me begin here. Okay, so here we have an equation where we got NO reacting with oxygen to give us nitrogen dioxide. Okay, now when we balance it, we had these coefficients we put up front, which now tells us that I was saying that, for example, I would say, okay, this takes 2 molecules of NO to react with 1 molecule of oxygen to give us 2 molecules of nitrogen dioxide. Now we can extend that and say, well, it takes 2 moles. Remember moles, Avogadro's number, 6.02 times 10 to the 23rd molecules. Well, 2 moles of NO require 1 mole of oxygen to give us 2 moles of nitrogen dioxide. Note the relationship between the two reactants. NO, it's a 2-to-1 ratio, okay? And from NO to nitrogen dioxide, it's a 2-to-2 ratio, basically 1-to-1. And if we look at oxygen to the product, that is a 1-to-2 ratio, okay? So we're going to use that information here in a few more slides. Bottom equation down here, we have nitrogen reacting with hydrogen to give us ammonia, NH3. Again, with that coefficient, or what? That's the coefficient we use to balance the chemical equation. We can say that if I have 1 mole of nitrogen, I need at the minimum 3 moles of hydrogen gas. And when those two react together, I'm going to create 2 moles of ammonia. So bear in mind, the last chapter we talked about molar mass, where we added up all the atoms involved in the compound. And that molar mass had the units of grams per mole. Now that we figure out how many moles we have of something, we can actually now calculate based on the molar mass how many grams of material we make, okay? So we need a balanced chemical equation, and if it's not balanced, then obviously your calculations will be incorrect, all right? So the coefficients gives us the mole ratios. Now, refresh back to your memory when we talked about conversion factors. And I emphasize the point about ratios. Ratios, be it dollar per hour, be it miles per hour, now grams per mole, any ratio can be written one or two ways, okay? And I demonstrated that. Well, we have a ratio here. We have a ratio of 1-to-2 for nitrogen and 1-to-3 for nitrogen and hydrogen. Remember, even though there's not a number in front of nitrogen, it's understood to be a 1, okay? 1-to-3. So we can write it with nitrogen in the numerator and hydrogen in the denominator, 1-to-3. Or invert it. We could write it with 3 hydrogens in the numerator and 1 nitrogen in the denominator, okay? And during that time when we were talking about conversion factors, I said keep track of your units. Well, here we are, okay? Because the same thing can be applied here. By keeping track of your units, that would assure you that you got the problem set up properly. Okay, let's take a look at this reaction here. This reaction is 1 mole of iron 3 oxide, okay, reacts with 3 moles of carbon monoxide to give us iron, 2 moles of iron, and 3 moles of carbon dioxide. So the mole ratio between carbon monoxide and iron 3 oxide can be written in this manner, where we got iron 3 oxide in the numerator and carbon monoxide in the denominator. Or we can just simply invert it, where you got carbon monoxide on top in the numerator and iron 3 oxide in the bottom, okay? Now we're not just limited to the reactants, okay? If we look at this ratio right here, where we got 2 moles of iron per 3 moles of carbon monoxide, well, that's that relationship. Come on. That's that relationship between these two right here, okay? And you have the relationship between carbon monoxide and carbon dioxide, which is a 3-to-3 or 1-to-1, okay? And so every one of those relationships or ratios can be written 1 or 2 ways. And which way you write it depends on the question that's being asked. So let's take a look at the first problem. They're asking you here, how many moles of iron can be formed from 10.2 moles of carbon monoxide, okay? So we are given 10.2 moles of carbon monoxide and we need to know how much iron we're going to make. So we are only concerned about these two right here, okay? Don't really care about the other ones because they're not asking you a question about the other ones. So we're looking at that ratio. We can see there's 3 carbon monoxides to 2 irons. We're going to need that bit of information to set up our problem. Go. I forgot that. So when we set up the problem, we're given 10.2 moles of carbon dioxide. The factor in the center here, next one, is that mole ratio that comes from the balanced chemical equation. Note that we can cancel, let me clear it up a little bit here. We can cancel moles of carbon dioxide in the manner you will set up properly because we're looking for iron. So iron stays in the numerator. So unit-wise, we're going to end up with moles of iron, which is what the problem asks for. Okay? Now it's a matter of doing the math and taking 10.2 times 2 divided by 3 would give you 6.80 moles of iron 2. Be aware of your sig figs. I got 3 sig figs here, 10.2, so my answer should have 3 sig figs. Okay? All right, now let's take a look at the second problem. In that scenario, they're asking you how many moles of iron 3 oxide are needed to react or form 17 moles of carbon dioxide. Okay? And so here we're only concerned about carbon dioxide and iron 3 oxide. So we need to make 17 moles of carbon dioxide. How much of iron 3 oxide we need to make? Okay? That's what they're asking you there. Oh, there you go. One more to let in. Okay. So everything else is out of concern. It's only those two based on the question. We note the ratio. 1 iron 3 oxide for every 3 carbon dioxides. Okay. So we set up the problem as follows. Okay. 17 moles carbon dioxide is what we're given. The 1 mole of iron 3 oxide for 3 moles of carbon dioxide, that comes from the balanced chemical equation. Note our units, carbon dioxide cancels out, leaving us with iron 3 oxide. Now, to do math, it's 17 divided by 3. Your answer is 0.7 moles of iron 3 oxide. We're dealing with moles here. Remember, mass has a unit number. So if we figure out the mole mass of iron oxide, we can become moles. Because in the lab, we're not measuring moles. We are measuring grams, pounds, or kilograms, or whatever. We don't measure moles directly. We have to measure in grams. When we measure in grams, based on the molar mass, we can convert that to moles. Okay? All right, let's take this one. Well, you may be given a reaction here where we got sulfur dioxide reacting with oxygen to give us sulfur trioxide. Okay? Well, if we stick a 2 there, it gives us 4 oxygens. We're good with oxygens on the reactant side because I got 2 coming from sulfur dioxide and 2 from oxygen, but our sulfur got increased. So we got to put a 2 in front of SO2, sulfur dioxide. Okay. Now check to see if we're balanced. We have 4 oxygens from sulfur dioxide, 2 from oxygen. That gives us 6. 2 sulfurs. Okay. Look at the products. We got 2 sulfurs and 6 oxygens. We got a balanced chemical equation. Okay. It's understood there's a 1 here. All right. So keep in mind our relationship between sulfur dioxide and oxygen is a 2 to 1. Our relationship between sulfur dioxide and sulfur trioxide, it's a 2 to 2 or a 1 to 1. The relationship between oxygen and the product is a 1 to 2. Okay. So with that information, we can, look at the first problem. They're asking us how many moles of sulfur trioxide will form if 0.165 moles of oxygen react. Okay, of oxygen react. So what we're concerned about is simply the relationship of sulfur dioxide and oxygen. Okay, that's all we're concerned about based on the question. That ratio is a 1 oxygen per 2 sulfur trioxide. With that a bit of information, we can set up the problem now. Okay, we write down what we're given from the problem, 0.165 moles of oxygen. This comes from the balanced chemical reaction. It's 2-to-1 ratio. Notice that our oxygens cancel out unit-wise, leaving us with moles of sulfur dioxide. Therefore, let me erase that because it's getting a little messy. Therefore, our units that we are left with are moles of sulfur trioxide. Now you simply do the math, okay? 0.165 times 2, you get 0.332, okay? So it stands to reason when you think about it that the ratio is 1 to 2. So whatever number I have of oxygen, I'm going to need twice that for sulfur trioxide. If I have 10 billion molecules of oxygen, I need 10 billion times 2 of sulfur trioxide because the relationship is a 1 to 2. Okay, now the next one says, let me erase some of this. How many moles of sulfur dioxide are needed to make 0.42 moles of sulfur trioxide? And so what we're concerned about is the relationship between sulfur dioxide and the product sulfur trioxide. That's all we care about based on the question. Okay? And we look at the coefficient, it's 2 on both sides. Basically, it's a 2 to 2 ratio or 1 to 1. Okay? Because the 2's will cancel out once we set it up. And so you can see here that we're given that amount of sulfur trioxide from the problem. This is from a balanced chemical relationship. That's what we call the stoichiometric relationship, which is 2 to 2. And you can see that sulfur trioxide units cancel out, leaving us with sulfur dioxide. So in this case, for this reaction, if I start off with 0.42 moles, if I need to make 0.042 moles of sulfur trioxide, the product, I need the same amount of sulfur dioxide because the relationship is a 1 to 1 or 2 to 2. Okay. So all these problems here, we need that balanced chemical reaction. Okay. This particular flow chart kind of summarize it for you. I got another one coming up that gives you more information. But in order for us to be able to go from A to B, whatever A and B is, and I don't mean just going in one direction, but going left and right, we must always have to go through moles, okay? That is the common unit that compounds have with each other in chemical reactions. And if we're given grams of a material, whatever A will be, if we know the molar mass, of A, and we divide by the molar mass, we get moles. Moles given, that is what we're given in the problem. Excuse me. Okay. From the balanced chemical reaction, we get the mole ratio. Okay. Be it 1 to 1, be it 2 to 1, 3 to 4, whatever the balanced chemical reaction tells us, From the mole ratio, then we get the number of moles of what we're looking for, or what we're finding, what we're trying to calculate. And from its molar mass of what we're looking for, we can finally get to the grams of the material, okay? So refresh your memory on molar mass and how to calculate it. A lot of times it's not molar mass, it's just the atomic weight if it's just the element, okay? But the molar mass, you need to add up all of the elements in that compound, add them all up, their atomic weights individually, and how many of each, and that gives you the molar mass. Molar mass has the units of grams per mole. It's another ratio. So basically, if we have grams of what we're given and divide by molar mass, we get moles of what we're given. And then once we have moles of what we're looking for, what we're trying to find, when we multiply by the molar mass, we get grams, okay? So bottom line is to get from point A to point B, you gotta get into the moles. So let's take a look at this example here. In this example, we have iron 2 oxide, okay? Now, how do I know it's iron 2 oxide? Because oxygen or oxide has a -2. That means the iron must be iron 2. In this process, it's reacting with aluminum, iron 2 oxide reacting with aluminum to give us iron, elemental iron, and aluminum oxide, okay? This is an example of a single replacement reaction. Refresh your memory in that chapter, okay? If you look up the metals as far as in the activity series, you'll find that the aluminum is a lot more reactive than iron, okay? And then the next question you ask, is that the most reactive metal in compound form? No, it's not. It's in elemental form. So therefore, this reaction proceeds as written. Okay. This is a single replacement reaction. With that bit of information, now you balance it and you end up with the ratio that says I got 3 iron, 2 oxides for every 2 aluminums, which will give me 3 irons and 1 aluminum oxide. Okay, that's our stoichiometric relationship there. So you may be asking questions as follows. Calculate the mass of iron 2 oxide needed to completely react with 5.5 grams of aluminum. Okay, well, break that question down. What exactly is it asking for? It's asking for the mass of iron 2 oxide. So this guy, okay? And it needs to react completely with 5.5 grams of aluminum. So we're only concerned about the reactants. If I start off with 5.5 grams of aluminum, how much iron 2 oxide do I need? Is what the question is being asked. It has nothing to do with the products. Don't care about it based on the question. We're looking at the reactants here, okay? Or you may be asked a question like this, where it says, calculate the mass of aluminum oxide. Let me erase the other stuff. Calculate the mass of aluminum oxide produced if you start off with 10.25 grams of aluminum. So in this case, we're wanting to know how much aluminum oxide we make if we start off with 10.25 grams of aluminum. So those are the only 2 we're concerned about. Next thing I do is look at the ratio. It's a 2 aluminum for every 1 aluminum oxide. Okay. So let's run through them. So same reaction. First part, we start off with 5.5 grams of aluminum. Okay. We're in grams. We have to get to moles. Okay. We can't do anything without getting into moles. So this is the molar mass, in this case, the atomic weight of aluminum. So you simply look that up on the periodic table. you'll find it to be 26.9 grams of aluminum. Okay. Notice something. Keep track of your units. Look at this. Grams of aluminum are being canceled out the way it's set up. So you're on the right direction. Okay. Next thing, we get the stoichiometric relationship between what we're looking for, which in this case is the iron 2 oxide. Okay. And it's a 2 to 3 relationship. Again, keeping track of your units, look at this. The moles of aluminum cancel out. So if I were to stop the reaction here, is the calculation I should say, I would have unit-wise moles of iron 2 oxide. But the problem wanted you to go all the way to figure out how many grams. So I need one more factor, okay? And that factor converts the moles of iron 2 oxide to grams based on the molar mass of iron 2 oxide. And that is 71.85 grams. Keeping track of units, you see they all cancel. So unit-wise, I end up with grams of iron 2 oxide, which is what the problem asked me to do. Now, it's on you to do the math. 5.55 divided by 26.98 times 3 divided by 2, etc. You should come up. Let me erase this real quick. Your answer should be 22.2 grams of iron 2 oxide. So if you start off with 5.5 grams of aluminum, I need at the minimum 22.25 grams of iron 2 oxide for this reaction to proceed as written. Okay, second part, you were given 10.25 grams of aluminum again, okay? While we're in grams, we need to convert that to moles. So atomic weight of aluminum, okay? Here, the second question asks you, how much aluminum oxide am I going to make if I start off with 10.25 grams of aluminum? So I need the stoichiometric relationship between aluminum oxide and aluminum. Notice that unit-wise, follow the units, they're canceling out properly, leaving me at this point with moles of aluminum oxide. Now I need to convert that to grams of aluminum oxide, so I need the molar mass of aluminum oxide, and that is 101.96 grams. Again, 2 aluminums, 3 oxygens, that adds up to 101.96 grams. Note the units of molar mass, grams per mole. Okay. Follow my units again. Everything's canceling out. Unit-wise, I'm at grams of aluminum oxide, which is where I want to go product because of the question. And keeping track of your sig figs, and you end up with 19.37 grams. So if I start off with 10.25 grams of aluminum, I should make 19.37 grams of aluminum oxide. Okay. Now this one here, this flow chart kind of puts it all together. Okay. Now, for the ones in the bottom left and the bottom right, the ones in yellow, that is only true if you are under STP conditions. Remember, 0 degrees Celsius, excuse me. Yeah, let me erase that. Only at 0 degrees Celsius, that's supposed to be a degree, and at 1 atmosphere. My thumb's too big, but you get what I'm trying to write there. Okay. That only in those conditions is this relationship true. Okay. But if you're starting, you're given grams of any material, and I need to figure out the volume if it's a gas, I need to come over here to the bottom right. What I need to do is I need the molar mass, which will give me the moles, which based on the reaction will give me the mole ratio, which will give me the moles of whatever I'm looking for, which finally if I'm at STP in this relationship, I got the volume. Okay? So I can go from any direction. I can go from here to here, okay? Or reverse, starting from here back to 2 grams, or any direction thereof. I can go from grams given to grams fine, okay? Or I can go, it's going to get a little messy, but I think you get the gist of it. I can go this direction, okay? I can go this direction. I can go this direction, not only in the forward, in the backward, okay? The main point here is I can't go anywhere without getting everything into moles. And furthermore, I can't get the right answer if I don't have a balanced chemical reaction. If it's not balanced properly and the ratio is, say, 1 to 2, but you balance it as a 1 to 1, obviously your number would be incorrect. So you got to make sure you have a balanced chemical reaction and then get into moles, okay? And that's the only way I can get from apples to bananas if I go through moles. Right. So here's an example of a reaction. Now this chapter is going to be fairly short. We'll probably get about 3 or 4 more, and that's about it. But there's a lot of problems on the worksheet. There's a lot of previous homework that's on the course website. Do jump on in and take a look at it. Okay, in this case, they're asking you write and balance the reaction of hydrochloric acid and solid cobalt. They give you a bit of more information. They tell you, I can't see it here. They tell you that cobalt ends up with a +2 state. Why they tell you that? Because cobalt is one of those metals that we don't know the oxidation state. It could be 2, it could be +4. So they're telling you that. Okay? So what we got to do is first write the reaction. Hydrochloric acid, HCl, and cobalt, okay, reacts to form cobalt chloride, actually cobalt 2 chloride, plus hydrogen gas, okay. After we balance it, we end up with 2 hydrochloric acids and 1 cobalt, which gives us 1 cobalt 2 chloride and 1 hydrogen gas, right? Okay. They ask you the question here. How many liters of gas at STP will form if you have 5 grams of cobalt reacting? So mark what you're looking for, okay? That way you keep track of where you need to do. They want to know how many liters of gas. Well, the only gas here is obviously hydrogen, okay? And if you start off with 5 grams of cobalt. So those are the only 2 you're concerned about. Okay, notice that ratio is a 1 to 1. Plus, notice that you are at STP. So that bit of information would be helpful. All right, so we write down what we're given. 5 grams of cobalt. Remember, we gotta get into moles. So we need the atomic weight in this case, because it's the element cobalt, to give us moles of cobalt. Okay, now we need a conversion factor from the balanced chemical equation that relates cobalt to hydrogen. So it's a 1 to 1 relationship. Notice again, as you're keeping track of your units, moles of cobalt cancel, grams of cobalt cancel. So at this point, if you did the calculation, you will be at moles of hydrogen. Okay. Question asks volume, how many liters of gas? So we need one more bit of information. And since we are at STP, we can then utilize that relationship only because we are at STP. Okay, so 22.4 liters per mole. That being the case, we do the math, note my units again, They're canceling out, leaving me with liters of hydrogen gas, which is where the problem told us that we're trying to calculate. So if I start off with 5 grams of cobalt and it reacts with sufficient hydrochloric acid, I should make almost 2 liters, 1.9 liters of hydrogen gas. Okay. All right. Excuse me. This question says, how many, let's erase some of this. How many liters of hydrogen gas form, oh, excuse me, I misread that. If 2.374 liters of hydrogen gas is formed, how many grams of hydrochloric acid reacted at STP? And so if we made 2.374 liters of hydrogen gas, the question is, okay, how much hydrochloric acid reacted? So we're only concerned about those two. Note the mole ratio, it's 2 to 1, 2 hydrochloric acids per 1 hydrogen. Then we're still at STP, so that bit of information would be useful. Okay, so we write down what we're given. We're given 2.374 liters of hydrogen gas. Again, we got to get into moles, so we got volume of hydrogen gas. We can utilize the 22.4 liter relationship per mole. That would give us moles of hydrogen. Okay. Then we slap in the mole ratio between hydrochloric acid and hydrogen. That comes from the balanced chemical equation. It's a 2 to 1 ratio. Okay. Notice again, keeping track of your units. They're canceling out properly, leaving me with moles of hydrochloric acid at this point. But they're asking you how many grams. Okay. So I need one more conversion factor, and that is the molar mass of hydrochloric acid. Okay. Now, checking your units, you can see moles of hydrochloric acid cancel, giving me finally unit-wise grams of hydrochloric acid. Doing the math, that is 7.72 grams of hydrochloric acid reacted if I started off with 2.37 grams, liters of hydrogen gas. Notice something, there's 3 sig figs there, but we started with 4 over here, okay? Question might be, okay, why 3 sig figs? Well, remember I said, as far as atomic weights, molar mass, don't use those for determining sig figs because they come from whole numbers and you have an infinite number of sig figs, so we don't use the atomic weights or molar mass. The mole ratio, those are whole numbers, they're constant, they're exact numbers, so that's not a factor. This relationship here, 22.4 liters, is a measurement and therefore would play a factor in your sig fig calculations. Since there's 3 sig figs, 22.4, your answer should have 3 sig figs, even though you start off with 4 sig figs with 2.374, okay? So 22.4 liters per mole can play a factor with your significant figures because it's a measurement. All right, here's this one. Another word problem which needs you to convert it to a chemical reaction. It's saying here that hydrochloric acid gas plus oxygen produces chlorine gas and water vapor, okay? And they're asking you how many liters of chlorine gas can be formed if 3 liters of oxygen react completely at STP. Well, before we do anything, we need a balanced chemical reaction. So based on what we're given, hydrochloric acid reacting with oxygen gives us chlorine gas and water. Okay? Everything's in the gas phase. So the states are on G. And now we go back and balance it, and you should end up with 4 hydrochloric acids, 1 oxygen, 2 chlorine gases, and 2 waters. Okay? Now, based on the problem, they're asking you how many liters of chlorine gas are formed, okay? How many liters of chlorine gas are formed if 3 liters of oxygen completely react? So we're only concerned is oxygen and chlorine gas, okay? Which happens to have a ratio of 1 to 2. We'll keep that in mind, okay? Plus, we're at STP. So 22.4 liters per mole could be a factor here too in our calculations. So we write down what we're given, okay? First one, you always got to get to moles. So since we're at STP, we can use this factor to get us into moles of oxygen. The next factor, based on the balanced chemical equation, relates oxygen to chlorine, which is a 2-to-1 ratio, okay? Keeping track of your units, you'll see it, okay? That chlorine, moles of chlorine gas are what are left at this point, okay? But we need one more. Since we're at moles of chlorine, we need to convert it back to volume because the question asks us what the volume is. That being the case, since it's a 2-to-1 ratio, it's simply double the volume of oxygen, okay? Now notice something here interesting. When you are dealing with gases, and I repeat, gases only, everything's in the gas phase, and you're at STP, notice that our conversion factor of 22.2 liters per mole, they cancel each other out, okay? So you could leave them out if you want, but if not, until you're comfortable with it, leave them in. But when you're dealing with all gases, and you need to go from one to the other, you just simply need the stoichiometric relationship between the reactants or the products, okay? But only if they're all gases and only if you're at STP. All right. Try these at home, okay? This is something you can try out. So work it through. I'll give you the answer here in a second, but see if you can work it out on your own. They're asking you here, it says carbon reacts with oxygen gas to form carbon monoxide, okay? So that's the reactions. You write the balanced chemical reaction for that. Then they're asking you how many liters of carbon monoxide at STP can be made if, remember first part of the question, if you start off with 15 grams of carbon, calculate that. And then the second one, if you start off with 20 liters of oxygen gas, okay? That being the case, you should end up with 28.0 liters of carbon monoxide for the first question and 40 liters of carbon monoxide for the second question, okay? So work through that. Make sure you understand it. You're going to get a lot of those lights, okay? All right, kind of an overview of that. We talk about elements on the graph. We talk about these compounds. So the elements we create covalent, right? From that information, we also learned how to name them and so forth. These compounds we put together to write reactions. Then we talked about balancing these reactions, okay? So from the balanced reactions, now we're able to know the stoichiometric ratios between reactants and products and so forth. With that bit of information, we're able to calculate reactants or products based on the ratios, and we can give it in terms of moles, grams, or liters, depending on the question, okay? But everything here to get to point A to point B, the important part is moles. We cannot get from one point to the other without moles, okay? And this chart, this flow chart, really summarizes this chapter on how to get from point A to point B, okay? So if we're given grams and we're trying to find out the grams of a product and or reactant, we have to go through this pathway, okay? From the molar mass, we get the moles given. From the mole ratio of the balanced chemical equation, we're able to figure out how many moles are what we're looking for. And from its molar mass, we're at grams, okay? But we're not limited to that because we can go any direction from grams given to volume, going from top left to bottom left, okay? But only at STP, okay? We can go from grams given all the way over to gas, volume of gas, if we're at STP, okay? Now, I'm going from left to right, but keep in mind, you can start here and go back, okay? It's a two-way street here, but everything doesn't go anywhere unless you are in moles, okay? And you have to be in moles to get from point A to B or from B to C, right? And so learn how to calculate moles, having the molar mass. Learn how to use the molar rate. Remember that STD, you can go from moles to liters, different recipes, okay? And not just limited to math, you can start from here, go this direction. Let's go a little under. Any comments here? All right. How do you guys see that? So that flow chart, will really similar to your chart and have it from right into the product, okay? I just wrote you that they're getting okay, bye. I'm getting some of this. And I got it, and I can use it anytime. Other than that, we have a price. I'm here for Q&A. I'll see you later. And I want to do more as an instrument course. The recommendation is I can read the memory about 4 bucks. Okay. You pass the concept about 40, the lower that, 14 should be in here. Okay. 15 is another short one, so you shouldn't say I'm going to go right on the video. Okay. All right. So you see up there, I'll hear others. If you have a question, feel free to shoot on here real quick.